In this section, we will briefly explore SDN's control plane, a network-wide central logic that controls SDN-enabled devices' generalized forwarding, as well as device configuration and management. Traditionally, the network layer functionality has been implemented in a distributed per-router approach. In this architecture, a monolithic router that contains the switching hardware also runs proprietary implementation of Internet standard protocols like IP, RIP, ISIS, OSPF, and BGP. Although these protocols are open, they are implemented and adapted by manufacturer of the routing device for its hardware and OS. The functionalities like firewall, load balancer, NAT, and other similar middle boxes were also packaged into specialized hardware. While the per-router implementation and hardware dependence does not change for the forwarding part of the work that is done in the data plane, in software-defined networking, the control is no longer performed in each router. Software-defined networking could be described by 4 key characteristics. First, flow-based forwarding. This means that forwarding could be based on a number of header fields that allow classifying and decision-making on the packet that belongs to a flow. This is opposed to destination-based forwarding that decides solely based on destination of each packet. Second, separation of control and data plane. Devices in data plane that perform matching plus action are separated from the controller software and servers that determine and manage the flow tables. Third, control functions are external to data plane. The control plane is software-based and is often a distinct remote controller that interacts with local controller agents in routers to compute their forwarding tables. And fourth, the programmability of the network, which is possible due to software-defined nature of the control plane, allowing defining applications with a standard interfaces to talk to and configure network devices. What are the benefits of moving towards a centralized controller? The centralized nature of the SDN helps avoid router misconfigurations and improves flexibility of traffic flows. The distributed nature of running routing algorithms in each router and converging to a network-wide decision on paths is a complex functionality. Running the same program in a centralized way is comparably easier. Software-defined networking also allows for non-proprietary implementation of the network functions in the control plane. We can compare the move from per-router control plane to software-defined networking to the move from mainframe to PC. The routers, like mainframes, have a specialized applications running on a specialized operating systems running on specialized hardware. Everything is vertically integrated, closed, proprietary, therefore causing slow innovation confined within the providing industry. With software-defined networking, similar to the same shift that happened from mainframe to PC, the hardware, the operating systems, and applications are separated. Therefore, shifting towards allowing for horizontal scale, open interfaces, fast innovation, and more people involved in development of new and upcoming technology. Let's discuss another motivation for software-defined networking: traffic engineering. One of the driving forces towards software-defined networking is fine-grained control over the network traffic. Let's discuss it through an example. Consider a network with nodes U, V, W, X, Y, and Z with given link costs. Remember the destination-based forwarding procedure we examined on this network. Now, what if the network operator within this network wants X to Z traffic flow XYZ and U to Z traffic flow along UVWZ and not use the XYZ. In traditional per router control plane, which works based on least cost path selection and destination-based forwarding, this is not readily available. On the same network, what if the network operator wants to split U to Z traffic along UVWZ and UXYZ to perform load balancing? Similarly, this is not readily available by least cost path selection and destination-based forwarding. Another example on the same network. What if W wants to route the yellow traffic on the figure directly to node Z, but needs to route the blue traffic through Y? We discussed policies that could be used for doing this kind of decisions. But remember, those policies were not applicable in intra-AS routing. And destination-based forwarding, as done in link state and distance vector routing, could not help this. So, what shall we do? These are all possible through software-defined networking.